Okay, so I am just a little bit behind. We're not behind, but in terms of getting all my stuff together. Last time, what we had done was we had talked about, I had introduced a two-way analysis of variance. And we had put up the Anova table, and what I've done, I've not posted it yet on the web page, but I've done a small, I think it's 10 minutes or something like that, video on doing the two-way analysis of variance in R. So it gives you the script inside that video. I will post that today or tomorrow. I will also post the data set that goes with that video clip. And importantly, I make a few points in that video about the box plots because boy, did I even talk about a data set? I don't think that I did. The data set that we were looking at, there were two different varieties of seeds. So we had seed type, and there was seed type 1 and seed type 2. And then there were 3 levels of fertilizer. So there was low, medium, and high. And I give, how many observations are there in each? 1, 2, 3, 4, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. And a couple of points, I include the data set in an Excel file on the web page. And I also include, I will include, it's not up yet, but I will include the CSV file that you need, which takes these data and then reorganizes them. So in the Excel file, when you open up the page, it looks exactly like this. In the CSV file, because of the way R is handling data, it all has to be in a column. So I have a column that says seed, and then a column that says fertilizer, and then a column that says yield. So here I have seed type 1, fertilizer, L, and then whatever the number is. And then seed type 1, fertilizer, L, and then whatever the number, and I go all the way down the column. Okay? Now, I think the way I've set it up, instead of having seed type number 1 and number 2, I have 1 and 2. And here I have, it's either L, M, and H, or low, med, high, something like that. But the important thing is when I do it that way, and I open it up in R, because this is not a number, right? It's a word. R automatically treats it as a factor. So it's not trying to do a regression with it, it's treating it as a factor in an analysis of variance. So that makes life a lot easier. And if we look at the model, remember what the model is. Our model is yijk is equal to mu plus alpha I plus beta j plus alpha beta ij plus epsilon ij. Let's see, how many subscripts do we need? Seed, fertilizer, so epsilon ijk. Okay? So in R, how do you do that model? Well, I have yield, and we have to be careful about capitalizing and all of that. If I capitalize it here, and then when I write the code, I don't capitalize it, it's not going to like that. Okay, so I need to make sure I keep everything in the correct case. But yield is a function of seed FERT plus FERT plus, and then I do seed asterisk FERT. Okay, and then that'll give me the Anova results, which is simply the sums of squares of degrees of freedom. And then what you have to do after you've done that is you have to take that Anova statement and ask for the summary. So it's summary, paren, and then inside the parens you include that AOV statement, and then it gives you the full Anova table. Kind of. Okay? It doesn't give you everything. There are a couple of things that it doesn't provide, and I'll talk about that in just a few minutes. Okay? All right, so when we run that analysis, and here's what the Anova table should look like. This example comes out of a wonderful book. I actually, years ago when I was here at SEMO, this was the required textbook for this class. Applied Statistics, Analysis of Variance and Regression by Dunn and Clark. It's a wonderful book. And it has this example in there. And the Anova table looks like this. We went through the development of the Anova table last time, but I don't think I gave you the numbers that go in there. So let me just give you that now. So we have source, sum of squares, degrees of freedom, mean square, expected mean square, and then F computed, and then F tabled. So the source was do seeds, do fertilizer, then do seed, by fertilizer, air, and total. Total. Okay, and the what we get for do seeds, the sums of squares is 77.4, 99.9, 44.1, 22, and 234.4. Is that a 9 up there? That's a 4, 77.4. Okay, degrees of freedom, I get 1 because I had 2 types of seeds. 2 minus 1 is 1. Fertilizer, I had 3 levels of fertilizer, so I should have 2 degrees of freedom there. Degrees of freedom here is A minus 1 quantity times B minus 1. All right, so it should be 1 times 2, so it should be 2. Air degrees of freedom, I have 18, and then total, I have 23. So 18, 20, 22, 23. Yep, that works out. Then, for my mean squares, 77.4 divided by 1 is 77.4. 99.9 divided by 2 gives me 49.9. 44.1 divided by 2 gives me 22.1. And then here, 22 divided by 18 is 1.2. The expected mean squares are sum of E squared plus (12), which is going to be EN, right? Plus BN sigma A squared. B, right? I had 3 fertilizer levels, right, which is B. And then N, 4 observations, so 3 times 4 is 12, so B times N is 12. I'm going to have sigma E squared plus A n sigma B squared. Here I'm going to have C times fertilizer, so sigma E squared plus, let's see, what should that be? There I have sigma E squared. What do I get there? I have 2 seed types, 3 fertilizer. What should that be? That should be just n sigma A B squared. Okay? So then the F test for seed type is this divided by that. The F test for fertilizer is that divided by that. The F test for the interaction term is that divided by that. All right? So if we compute those, the computed F is going to be 63.3. So that divided by that is 63.3. That divided by that is going to be 40.9. And that divided by that gives me 18. And my table values are 4.41, 3.55, and 3.55. So all my factors are significant. Okay? And it turns out when you run it in R, that's exactly what you get. So that's good news. Okay? All right. So now, one important thing that R does not give you, and that's the coefficient of determination. So what we would like to know is how much of the variance in the model, or in the data, is explained by the model itself. So what is the model? The model is yijk equals mu plus alpha I plus beta j plus alpha beta ij plus epsilon ijk. In other words, how much of the variation is attributable to that part of it compared to the epsilon? Okay? How would you go about figuring that out? It's called the coefficient of determination, and it's simply the percentage of the variation attributable to the model in the data set. How would you approach it? Well, you know how much total variation there is. That's that thing right there. There's your total variation. Okay? You know that that right there is just noise. That's measurement error. Or it's just natural genetic variation in the seeds, or it's attributable to weather or rainfall, or all those other things that you're not controlling. So what's the R squared? It's called the coefficient of determination, and whenever you're doing an analysis of variance or a regression analysis, report the coefficient of determination. That's your first indicator as to how good this model really is. So R squared is equal to that divided by that. So the sum of those things divided by that. Okay? What is that? We have a little calculator here on this computer. Let's help. Use the damn phone. That's why God gave us these damn phones. Okay? Because they all have this little calculator thing on them. All right, let's see what that is. We have 77.4 plus 99.9 plus 44.1. Okay, that's 221.4. I'm going to divide that by 234.4. Divided by 234.4. And that equals 0.9445. So my R square is equal to 0.9445. In other words, almost 95% of the variation in the data is explained by the model. That, my friends, is damn good. Okay? That is an amazing R square. If you have morphological data, you're looking at bear skulls or wood roach body lengths or widths or something like that, your R square is going to be in a similar neighborhood. If you're working on physiological data, maybe your R square is up around 80%. If you're working on ecological data, man, the world is a pretty noisy place. Your R square is usually around, if you're really lucky, it's going to be up around 30%. If it's above 15%, good. Oftentimes it's below 15%. If you're looking at sociological data, it's usually 30%, 40%, 20%, somewhere in that ballpark. Okay? So it's what a good R square is sort of a function of what your discipline is, really a function of how noisy your system is. Okay, so that's one point I want to make. The next point I want to make has to do with these degrees of freedom. We had talked last time about doing a bigger design. So let's do a three-way ANOVA. So now we have y, I, j, k is equal to mu, I, j, k, l, mu plus alpha I plus beta j plus gamma k plus alpha beta. I'm going to dispense with all the subscripts. Plus alpha gamma plus beta gamma plus alpha beta gamma plus epsilon. Okay? So here I get however many treatments there were, -1 degrees of freedom. Here, however many treatments there were, -1. However many there were, -1. So if this is 3, and that's 3, and that's 3, then here I get 3 minus 1 times 3 minus 1. So 2 times 2, I get 4 degrees of freedom there. Whoops. So there I had 3, which really gives me 2, 2, and 2. So I'm going to have 4 there, and I'm going to have 4 there. Here I'm going to have 2 times 2 times, I'm going to have 8 there. So that means I've got 8, 12, 16, 20, 22, 24, 26 degrees of freedom locked up, not counting what happens there. Okay? And I have to have some degrees of freedom left over for the error term. So you can see as the number of possible interaction terms increases, the number of degrees of freedom gets partialed out very quickly. And very quickly you run out of degrees of freedom that you can give to the error term. So you very quickly find yourself in a situation where you can't do any statistical analysis at all. You don't have the degrees of freedom. So what do? Well, the solution is to look at all of these possible interaction terms and decide which of them you don't care about or which of them make no biological sense. Simply don't estimate those. Those degrees of freedom then end up in the error term. There's another very good reason for doing that, and that is when you write a paper and you have this complicated design, maybe you're looking at 5 different factors and you've run the analysis and some of these interaction terms are significant and some are not, and you're writing the paper and you've given the Anova table, you now find yourself in a situation where you have to explain all of these interaction terms. suddenly your paper goes from a nice tight 18 pages long to being like 40 or 50 pages long, and nobody wants to publish it because it's too long. So if it's not biologically meaningful, don't do it. If you don't care, don't do it. Okay, unless it's obvious that it has a big effect. Get rid of it. Don't look at it. Don't worry about it. Okay? Just look at those major effects, right? And those interaction terms that make sense, or so that you end up with enough degrees of freedom in the error term. Okay. So that's the halfway point in the semester. We've now done through ANOVA. We've skimmed the surface on ANOVA, but you've now been introduced to all the key designs, the most important designs, the ones that you're most likely to use. What we've not done are planned contrasts, which are all odd little variations on this sort of stuff. We've not done incomplete block designs, any of that sort of stuff. What we're going to do now is shift gears. There is the next logical step for analysis of variance is something called Anova, or ANOVA. So analysis of covariance. Okay? So that would be a system where you have a fixed effect, like seed type, and then you have another effect in there, like amount of rainfall. Okay? So one term here is fixed, and the other one is free. It's not fixed. Okay? There's an easier way to do analysis of covariance, and that's what I'm going to show you. So what we're going to do is we're going to think of analysis of variance, and we're going to keep it in the back of our heads, but we're going to add one thing to this whole system. We're going to relax, or we're going to change one component. And what we're then going to do is we're going to restructure the whole thing and see what we come up with. And at the end, you'll say, oh, hey, this part of it is all the same, but the underpinnings are going to be a little bit different, and that will then allow us to look at those factors that are varying. So let's do that. I'm going to use an example. It looks something like this. Here's what we're doing. We have some kind of system where we have a variable x, and there's some kind of relationship between variable x and variable y. And what we want to do is we want to describe that relationship. We think that there is some kind of cause and effect. Well, we thought that when we were doing the regression the analysis of variance as well. That's why we looked at seed type, because we think there's a relationship between seed type and yield. Or between fertilizer levels. We think there's a relationship between fertilizer level and yield. So that part is the same. Okay? This is the same thing we did in analysis of variance. We thought there was some kind of cause and effect, and we're trying to figure out if that's true or not. Now what we're doing, just a little bit differently, is we're saying we think we know what that relationship looks like. In ANOVA, we had no idea. We didn't make any claims about the nature of that relationship at all. But now we're saying, hey, not only do I think there's cause and effect, but I know what the basic shape of that relationship is. So what we want to do is develop the most parsimonious description of that relationship. So anybody here ever work in a factory, do piecework in a factory? Oh man, lucky you. That's one of those jobs where you get paid not by the hour, but by the piece you produce. Yeah, that's a real delightful experience, I'll tell you what, okay? Let's imagine you go to work for some company. I used to work for a company called H&L Tooth and High Precision Forge out in the City of Industry in Los Angeles. We made the teeth, the only company in the world that makes the teeth for earth-moving equipment. So you see a backhoe, the teeth on the backhoe, made by H&L Tooth and High Precision Forge, okay? And I worked there, and over the years I transitioned up to better and better pay and better jobs in the mill. Started off at the furnace, then moved from the furnace to being what was called a portable grinder. Right, so you'd shape these things after they came out. And then ultimately I became a punch press operator, which was a real hoot and a holler, okay? But the thing was, they would get an order for these things, and orders came in worldwide, and they would say, okay, we need 50,000 of these things. And they would have to schedule the work week. So what's this guy going to do? What's this guy going to do? How much overtime do we need? That kind of stuff. So imagine that's your job. You get an order for something, and you need then to schedule how many man hours you're going to need to complete that order. So let's look at some data. We have a lot size, and we have man hours. And maybe we've been working at this factory for a little while. We've been there long enough to have 10 production runs. So the first production run is 30 units, and it takes 73 man hours. Next production run is 20 units, and it takes 50 man hours. Next one is 60, and it takes 128. 80, 40, 50, 60, 30, 70, and 60. And over here we get 170, 87, 108, 135, 69, 148, and 132. There you have it. There's the lot size. This is production run 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 production runs. Here's how big the order was, and there's how many man hours it took to complete the order. Okay? All right, so the first step in all of this is let's make a scatter diagram of what those points look like. And this now is the first crucial step. What goes where? Lot size is going to go here. And then man hours on this axis. In other words, what I'm saying is that man hours depends on lot size. So when we do this analysis, this is the dependent variable, and this is the independent variable. There will be times in your career where that's not what you want. You want the flip of that. you maybe have man hours and you want to predict lot size. Okay? Well, that presents a problem. Okay? Because this doesn't depend on that. That depends on this. So we're going to have to, if that scenario arises, we're going to have to deal with it in a slightly different way. And we will. But for right now, this is dependent, that's independent. To simply flip the axes and run the analysis will give you the incorrect result. I, in my research, have had to do that a whole bunch of times, right? Flip those axes because I had this and I needed to predict that. So I had to treat it in a different way. Well, let's look at what those data look like. So we're going to have 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, okay? And here I've got, what do I go up to? I go up to, I'm going to make that 100, make that 50, make that 25, 75, 125, and then 150. Okay, so what do we
I
got?
got up to 170 for a lot size of 80.
Yeah. All right, let's start over. My top, all right, 200 to, there we go. So that's 100, there's 200, there's 50, there's 150, 125, 75, 25. Close enough for government work. All right, so let's plot some points. What do we say, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, 30 and 73, 30 and 73. 20 and 50. 60 and 128. 80 and 170. 40 and 87. 50 and 108. 60 and 135. 30 and 69. 70 and 148. And 60 and 132. Something like that. Okay? Hey! Well, that looks pretty damn good, doesn't it? Wouldn't it be sweet if we had something that looked like that in biological data? That would be awesome. All right. How can we describe that relationship? What would you do? If those were your numbers for your master's thesis, how would you proceed? You know you've got something. Your job now is to convince your committee that this is the real deal and they should give you this piece of paper. How are you going to describe that relationship? Well, you've all had not linear, you've all had college algebra in one flavor or another. What would best describe that relationship? I'll be getting in shit. That's what I'm looking for. Bornstein must have been in here at some point in his career. Every class that Bornstein ever teaches in, there's a meter stick. What should we do?
Make a trend line.
Yeah, put in a line, right? There's a good line right there. Got this bridge I'd like to sell you. And I got a used car too. Okay, it's awesome. You'll love this used car. You like that line? The line sucks, man. What's wrong with that damn line?
Doesn't follow any of the points.
It doesn't go through the points. Come on. My markers. There. Like that line better? Okay. So what's the equation of a line? Well, this is y, and this is x. What's the equation of that line? You learned that in, I think, second grade.
Y equals mx.
Y equals mx plus b. What's b? On the graph, where is b? There's b right there.
Yeah.
If that's 0, then that's b.
All right.
Okay? What's m?
Slope.
It's that thing. Rise over run. Okay? So that's the equation of a line. Awesome. Except that doesn't look very fancy or anything. It's not going to impress anybody. You put that in your thesis and everybody's going to think, oh yeah, great, second grade, terrific, so what? So you got to dress it up a little bit, make it look a little more serious, make it look like you're smart, okay? So what we're going to do is we're going to have y equals beta 0 plus beta 1 x, where beta 0 is that point right there, and beta 1 is the slope. Same damn thing, okay? Same thing. We're just going to use different symbols, different numbers. All right. Except that you know that when we measure stuff, we don't measure it perfectly. Sometimes we take the temperature of the water and we record it incorrectly, or the thermometer was off by a little bit or something, but we're not perfect when we measure stuff.
We need to add error.
Yeah, we need to. So let's see, in Anova we did y equals mu plus alpha I plus epsilon ij, or epsilon I, right? Actually, it's yij, alpha ij, there, okay? You see a similarity? Yeah, so I need to add plus epsilon ij. Epsilon I. All right. But you see the similarity between those two models, right?
Yeah.
They're basically exactly the same. The difference is that here I'm saying I know what the relationship between man hours and lot size is, and the relationship is a line. So my man hours is going to increase at that rate right there, at this rate beta, with increasing lot size. So now as the factory superintendent, we got an order for 70 units. I need to schedule that many man hours. So now I got to ask Billy Bob and Joe Bob and Ricky Bob and Billy Bob to work some overtime. Well, that's pretty easy. Great. How are we going to get there? How are we going to get there? Well, let's make a few observations. I'm going to put that up on the board again in just a little bit. That nice graph, not with the same level of care. Somehow, I want to fit this line to my data points. Okay? Here, I knew some stuff. Here, I said, well, I know what mu is. My best estimate of mu is y bar dot dot, right? And I'm going to do yij minus y bar dot dot, right? That's one side. Then on the other side, I get alpha I. And what was alpha I? Alpha I was yi minus, yij minus yi dot bar. All right, and then this was the epsilon term was, whoops, that's not right. It's yi dot bar minus y. What is it? What's alpha? The deviation of what from what? Deviation of the treatment mean from the overall mean. So it's yi dot bar minus y bar dot dot plus, and this is the deviation of the observation from the treatment mean, plus yij minus yi dot bar. So that was pretty straightforward, okay? So in our case here, we've got y, and y is the sum of a constant term and a part that is full of error. So that's constant, right? And there's my error. Well, the xi's are constant, right? The betas are constant. And what that means is the expected value of this term right there is going to be this plus the expected value of that. And what's the expected value of epsilon? The expected value of epsilon is 0. So the expected value of yij is going to be equal to the expected value of beta 0 plus beta 1 x of I, right, plus epsilon ij. Epsilon I don't need to worry about the j's, okay? Which then is going to be equal to beta 0 plus beta 1 xi. Because the expected value of epsilon is 0. Great. Okay. So how do we find that best model? We know what the average is going to be. Okay. How do we go about finding the best model? How many of you had calculus? Nobody's had calculus? Not even applied calculus or One person. Nobody else has had calculus?
Like an intro class, but.
You got an intro to calculus. There are two things that you learn in calculus. The two major parts of calculus are what? Calculus is basically divided up into two parts, at least in the first semester. What are the two parts? It's such a foggy blur you can't even remember. What are the two parts of calculus? You learn to do two things.
Derive equations.
Yeah. Derivatives.
Derivatives.
Okay? You're finding a derivative. What is the derivative? What's the derivative of x squared?
X times X.
No. 2x. What's the derivative of x cubed?
3X.
3x. Okay? The important thing is you have a function. Here's a function. What do you do? What are you doing? So here's f of x, and here's x. What are you doing when you take the derivative of that function? What are you finding? You're finding x squared. What shape is that? Yeah. What's the equation for that? Roughly, the shape of the equation. What is it roughly? Y equals what? You don't like my axes. Fine. I'll give you a new set of axes. Here's x, and f of x.
In this instance, it'd be y equals negative x squared plus something, right?
Yeah, yeah. Well, we could do that. Then what would it be?
X squared.
Yeah, y equals something x squared.
Or in
Okay,
this case, yeah.
great. So what's y equals 2x?
That's a line.
It's a line. So you've gone from a curve to a line. Not only have you gone from a curve to a line, but when you find x and do, what you're finding is the slope of the line that's tangent to that curve at that particular point. That's the whole reason for taking the derivative, to find the slope of the tangent line.
All right.
The hell do you care about what the slope of the effing tangent line is? Who cares? Here's why it's important. You guys remember, you guys don't remember, Ronald Reagan, or as he was affectionately known, Ronald Reagan. What is Reagan famous for? You are living through the consequence of Ronald Reagan today. I'm not saying Donald Trump is the reincarnation of Reagan. Donald Trump is Reagan's evil twin.
Reaganomics.
Reaganomics, which was what?
Trickle down.
Trickle-down economics. The idea that you give tax cuts to corporations and rich people, and with all the extra money they have, they'll hire more poor people.
It's almost like that's not how the real world works.
And what happened in the Trump's first term. Tax cuts. How big was your tax cut?
I actually started making more money from taxes.
Yeah, so it's hard to. My tax cut was a 6-pack of Coke. That's how much I could do with my tax cut. What was Trump's tax cut? In the hundreds of millions. His tax cut is permanent. Yours goes away next year. That thing was based on something called the Laffer Curve. Something that looks like that. And the idea was that if you cut taxes, right, suddenly you're going to end up way up here and the economy is going to grow like a rocket and everybody will have a job and everybody will have 2 colored TVs and 3 Jaguars and a Mercedes and we'll all wear 3-piece suits and get our hair cut at JCPenney's or something. I don't know what the deal was. But we'd all be rich.
The only way to do that is invest.
Well, what's the problem with this?
Goes back
It's
here.
not a function. The thing about a function is it has, for each value of x, it has only one value for f of x. For each value of x, we got 2 values. It's not a function. It doesn't work. One of the consequences of the fact that they're treating this non-function as a function is because they've gone down this road, this economic path that they think works, but it obviously doesn't. How do you know it doesn't? Look at what's happened to the deficit and or the stock market under people that follow trickle-down economics versus people that don't. So presidents that follow trickle-down versus presidents that don't. What do you discover? 2 things. First of all, the growth of the stock market is always higher under what kind of president? A Republican or a Democrat? What does your gut tell you? What would your parents say? What would your friends say? Which political party gets credit for managing the economy? The Republicans. And yet, it's under the Republicans that the stock market performs poorly and the deficit grows dramatically. It's under Democrats that the deficit grows slowly and the stock market grows rapidly, more rapidly. And we'll do that analysis in a couple of weeks. We will download data for the Dow Jones Industrial Average going all the way back to 1893. And you will do a special kind of regression. And you're going to compare Democrats versus Republican presidents and see under which group the stock market does better. It always does better under a Democrat. But you say, wait, the stock market under Trump has been great. Well, and Trump takes credit for it, even though what Trump did was just latch on to the continuation of the Obama thing. And then, of course, now, since the pandemic broke, the stock market has sort of leveled off. And why do the deficits grow? So I asked this guy, I have a friend who's sort of staunch Republican and all of that sort of stuff. And I asked him, why do you think it is that the deficit always grows under Republican administrations? And the answer is clear, because they spend more money on the military and on tax cuts. That money has to come from somewhere, and it comes out of the national budget. The other thing is, why is it that the stock market does better under Democrats and not under Republicans? Republicans are supposed to be such good stewards of the economy. And the answer is, they don't care about the stock market. The stock market isn't what they're focused on. What they're focused on is the amount of money directly, immediately in their wallet. Not the amount of money that's invested in business and things. It's what's immediate of interest to them. So their own, well, the size of their house, the size of their yacht, that sort of stuff. Okay? We will delve into that from a statistical point of view in a little while. All right, back to the subject at hand. Why the heck do I care about this function? Because here's what I want to do. I want to find the line that fits my points best. So here I have my data points. And I want to put a line through them. And I've already done that, and you've said, no, that's not the best line. And my question is, how the hell do you know it's not the best line? How do you know it's not the best line? Your gut, you can see it and you know it's not right. How do you know?
Because if you follow it off, it wouldn't, I guess two numbers get further apart.
But your brain gives you the answer. You look at it, you can feel it in your bones. You know it's not the best line. What is it that bothers you?
The line is far from the dots.
The line is far from the dots.
Okay.
Those distances between the line and the dots are big. If the line fit perfectly, those distances would be smaller, would they not? What are those things right there? What are those distances? Well, when we did Anova, we did this thing.
Oh, the error term?
Yeah. So that was the error term right there. Okay? Does that apply here? Hell yeah. That thing right there
Gives you a massive error term.
is error. That's epsilon.
Yeah.
Okay? There's another example of epsilon. There's F. Those are things we refer to as residuals. It's the deviation of the point from this line that we're trying to draw. So what's our model? Our model is y is equal to beta 0 plus beta 1 x I, so y i's, plus epsilon I. So let's rewrite this for what epsilon is. So yi minus beta 0 plus beta 1 xi is equal to epsilon. Okay? So what am I trying to do when I arrange this line? What am I trying to do?
Trying to minimize the error.
I'm trying to make epsilon as small as I possibly can. Okay? I want to make epsilon small. The smaller epsilon is, the closer my line is going to match all those points. So the way I'm going to do that is I'm going to define a function. My function, I'm going to call it q, is going to be equal to yi minus beta 0 plus beta 1 xi. Okay. Okay? There's my function. Except now what I'm going to have to do is I'm going to have to add it up across all i's. So I'm going to put that in parentheses, and I'm going to add it up, and I'm going to go from I equals 1 all the way up to n. Let me rewrite that. So I'm defining this function as q is equal to the sum from I equals 1 to n, where n is my number of observations, of yi minus beta 0 minus beta 1 x of I, and then I'm going to square it. The reason I'm going to square it is because I want everything to be on the positive side. I don't want to have to deal with negatives and positives, so I'll just square it. So now what I want to do is I want to choose a value of beta 0 and a value of beta 1, which is going to make that as small as possible. So the trick is choose values to choose to minimize q. Hey, we were just talking about that. There I have a function. I take the derivative of that function and it gives me the slope of the tangent line. This is a function. There's a function. Where's the smallest part of that function? Where is that function minimal? All right, what do you know? You know, well, what I need, what I know about from calculus is derivatives. And derivatives give me the slope of the tangent line. So what happens? What's the slope of the tangent line right here? Minus something. What's the slope right there? Minus something. Minus something. Plus something. What's the slope right there? What's the slope of that line? What is it? What's the exact number? I could go home and grab my little level and hold it up there to make sure it's absolutely perfectly parallel with the surface of the Earth at that point. What's the slope at that point?
Just be your x.
What's the slope of that line? Give me a number. What's the slope of this floor?
0.
Thank you, 0. The slope of that thing is 0. So the lowest part of that function occurs when the slope of the tangent line is equal to 0. Or, there the slope of the tangent line is also equal to 0. So when the slope of the tangent line is equal to 0, I know that I have either a minima or a maxima. How do I tell the difference?
The lowest point or the highest point?
Yeah, how do I know it's a minimum or a maximum?
When the other slopes are lower or greater than.
Yeah, well, that happens here too. You would take the second derivative. Okay? All right. Hey. So, let's take the derivative of this function to find out where the minimum is. Okay, but wait. You didn't do that in first semester calculus. What you did in first semester calculus was dx dt, right? So you took the derivative of a function with respect to one variable. But now we've got two variables. We've got beta 0 and beta 1. So what we need to do is we need to do this using partial derivatives. So instead of, we're going to take the partial derivative with respect to something else. Okay? That's easy. All we need to do is take the partial derivative of that function right there. We want the partial derivative of q with respect relative to the partial derivative of beta 0, and we want the partial derivative of q with respect to delta beta 1. So delta q versus beta 0 and q versus beta 1. When we do that, here's the result that we get. These are referred to as the normal equations. So if you ever take a probability class or a statistics class, rather than just the freshman, when you take a graduate statistics class and they derive the normal equations, that's when you realize that this universe is truly a bizarre place. It is really, truly amazing. And it's easy to understand once you go through this why it is that so many mathematicians are so highly religious. It's really kind of cool. So we have delta q, delta beta 0, and that's equal to minus 2 times the sum of yi minus beta 0 minus beta 1 xi, like that, and delta q beta 1, delta beta 1 is equal to minus 2 times the sum of xi times yi minus beta 0 minus beta 1 xi, like that. Okay? I have a system of two equations in two unknowns. So I'm going to solve those two equations. These are known as the normal equations. I'm going to solve them. And when I do that, I get the following. I get the sum of yi is equal to n times b0 plus b1 times the sum of xi. And I get the sum of xi yi is equal to b0 times the sum of xi plus b1 times the sum of xi squared. You're saying, great. Now what? Hey! It's kind of interesting, actually, if you look at it. Let's solve these things, okay, for b1. What is b1? b1 is equal approximately to beta 1. b0 is equal approximately to beta 0. So I'm substituting these values in because I want to figure out what value there gets me as close as possible to the true value right there. So now I have a system of two equations and two unknowns, and I just need to solve for b0 and b1. And that's easy. You ready? This is going to be kind of amusing. I'm going to erase these. b1, we'll start with the hard one, is equal to the sum of xi yi minus, let me make that a little bit lower so it shows up on the video. V1 is equal to the sum of xi, yi minus the sum of xi times the sum of yi divided by n, all of that divided by the sum of xi squared minus the sum of xi quantity squared divided by n, which is equal to the sum of xi minus x bar times yi minus y bar divided by the sum of xi minus x bar quantity squared. That looks a lot simpler. So now the question is, who sees something? What do you see? What something is sticking its head out of the whiteboard, screaming at you, going, hey, 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 look at me, look at me, look at me. What is it that's screaming at you? What do you see?
You can cancel the xi minus x bar.
That's squared.
Oh.
That's squared.
Yeah,
You can factor it out.
factor it out.
I could. And then what? You're going the wrong direction. What if I were to multiply that times 1? Let me write 1 in a different way. Let me write 1 like this. Is that equal to 1? Yeah, that's equal to 1. Ah, good. Now you see it. Concentrate on the denominator. What do you see in the denominator? Multiply that times that. What do you get? That times that is equal to the sum of xi minus x bar quantity squared divided by n minus 1. Have you ever seen that before? Hell yeah. What's that called? I think that was like day 1 this semester or something. The hell is that thing called? What is that thing? See, that's observed
Oh.
minus expected, quantity squared, standardized by something. What is that? That's a sum. That's a sum of squares, sum of squares. A sum of square deviations, the sum of squares standardized by something, which would make it kind of like a mean square sort of thing. What is that? Don't make me say it, man. You're gonna feel like shit. If I have to say it, you're gonna go home, beat yourself up, bang your head against the wall for 15 minutes, and then get falling down drunk. on Mad Dog 2020 or something. Probably won't come to class for the rest of the semester, fail, your life will be over. You'll end up on the street living under a bridge or something. What is that called, man? Okay, one last chance. You know, I mean, it's not my fault if you end up under a bridge. Okay, it's simply not my fault. It's called something equals that. What is it that equals that? It's the variance.
I remember that.
S squared, okay? Or if we replace x with mu, right, it's going to be sigma squared. That's the variance. We just spent 8 weeks doing analysis of variance, right? That's what we were doing right there the whole time. Sums of squares, sums of squares, sums of squared deviations, sums of squares, sums of squares. Okay, that's the variance term. That's why we call it analysis of variance. There it is. Hey! If that term is a variance term, what's that? Because you're going to end up dividing that by n minus 1 too, just like you have here. What the hell is that called? The only difference is up here you've got x and y. So you're looking how x and y are together. What is that called?
Covariance.
Yes, that's the covariance. In other words, all be dipped in shit. The best estimate of B1 is the covariance of x and y divided by the variance of x. You want to know how Excel figures out what the slope of the trend line is? It computes the variance of x, it computes the covariance of x and y, and finds the quotient. And there it is. It's that easy. That, my friends, is effing awesome. That thing right there is better than sex. You come up with something like that, and you see that, and you realize that, and you understand how awesome it is, you go, holy shit. That's intense, man. It's amazing. The best possible slope for this line is that right there. Easy peasy. And how do you get there? You define this function, you find the minimum of the function. All you're trying to do is minimize the error term, and lo and behold, it comes up with something so neat and so clean and so tidy and so pretty. There it is. That's as good as it's ever going to get in life. You're done now. You can go home. You can call it quits. You can commit suicide, whatever. This is as good as it gets, man. That's effing amazing. So here we are. Here are our data points. And here's our perfect slope. The slope is perfect. All right, I'll bring this point down a little bit. There, now the slope is perfect. The slope is perfect. What are we missing?
The opposite.
The intercept, right? The intercept is all screwy. So the next thing we have to do is we have to figure out what the other part of this thing was, that is the intercept. So let's do that. So the intercept, B0, is equal to 1 over n times the sum of yi plus b1 times the sum of xi. Well, that's easy. That's equal to the sum of yi divided by n plus b1 times the sum of xi over n. What's the sum of yi divided by n? This is another one of those, if you don't get it, you're going to go home and drink yourself silly and bang your head against the wall for 15 minutes. And what is it? What's the sum of yi divided by n? Okay. 1, 2, 3, 4 people in the class. How tall are you? In inches. What's your age? What's your age?
22.
22. What's your age?
33.
33. What's your age?
22.
22. What's your age?
22.
22. Okay. What's the sum? 99.
What is like residuals?
What's 99 divided by 4?
24.75.
24 something, yeah.
Yeah.
Okay, what is that number?
What's the mean?
Thank you. What are we doing here?
Oh.
Okay.
I'm a very
That is y effing bar, okay? That's y bar plus b1 times x bar.
Okay.
So b0 is equal to y bar plus b1 times x bar. So the best intercept, what this is telling you is that a solution to your line is the point x bar comma y bar. In other words, you know that your line is going to go through that point, x bar comma y bar. There's your line. There's your perfect slope. The slope is equal to the covariance of x and y divided by the variance of x, and the line goes through that point right there. It doesn't get any easier. That is the best fit line. This solution to the line, right, is derived via the method of least squares. So when we're doing this, we're finding the least squares line. We have a special name for that line. We call it the regression line. So we're deriving the regression line via least squares. We sometimes refer to this as least squares regression. There are other ways to do it. We can do maximum likelihood and all sorts of other ways, but this is the solution which gives you the most parsimonious description of the relationship between lot size and man hours, or between height and weight, or between whatever, you know, gas mileage and how fast you drive, or whatever it happens to be. Okay? And now you can appreciate the following fact. If you were to flip the axes and repeat this analysis, you can see that this, if you take the inverse of this, it isn't going to be the same as running the analysis with the axes flipped. Okay? It gives you a different answer. if you're going to flip the axes and you want to put the independent variable here and the dependent variable there, you're going to have to solve this problem in a different way. How would you do it? Easy. Instead of using the covariance over the variance, you would simply use the variance of y over the variance of x. And when you do that, instead of being called the least squares regression, it's called the reduced major axis regression. That is similar to what happens when you do a principal components analysis, which is a method that we'll get into in about 3 or 4 weeks or so. Okay? All right. So, we're going to take our data points. We're going to find the line that has the slope covariance of x comma y divided by the variance of x. And that line is going to go through the point, right, x bar comma y bar, like that. That's how easy it is to do that. All right. So, what do I have? Now what we need to do is ask the following question. I'm going to show you 2 scenarios. Here's my line. And there's my line. Here are my data points. Okay? Anybody into something called macroecology? Ever heard of macroecology? It's like the ecology of systems sort of thing. The guy who is one of the big proponents of macroecology is a guy named Jim Brown. Jim H. Brown, James H. Brown, not the musician, but and Jim Brown, I was in Mexico once at this conference, and he gave this paper talking about these macroecological principles. And he put up the scatter diagram, and the points looked like this. There were thousands of points, and the points formed this perfect sort of sphere. And then he did the regression analysis, and he looked at that line. And he spent this whole talk talking about the significance of that line. And I'm sitting in the audience going, you have got to be effing kidding me, right? There was a woman and he was using it to explain all sorts of patterns in mammals. And one of these patterns was the fact that for the most part, males are bigger than females in mammals, and all that kind of stuff, and And there was a woman in the audience, this Canadian woman, Gail Michener, who's this animal behaviorist, and she spent 40 years tracking, on a daily basis, a single population of Columbian ground squirrels up in Canada, in Alberta. And she has daily data on these things. They hibernate over the winter. She's got data loggers and all that sort of stuff in with the animals. She knows exactly what happens to every individual every day of the life of that individual. And she's been doing that for 40 years. It is a data set which is unbelievable. And she's in the audience. And Jim Brown, who is full of himself, finishes this talk and he says, well, there it is. Any questions? As though anyone could possibly have questions. And Gail Mitchner stands up and goes, yes, I have one. And she just nails his butt to the wall. She just starts pointing out counterexample after counterexample after counterexample and explaining why this is nonsense. And she finishes by saying, and by the way, what's the R squared for your line? And the R squared was like 0.05%. And she goes, was it significant? And he responded, well, almost. So, let's look at those two scenarios, okay? Both of them you derive by the method of least squares. One of them looks awesome, the other one looks like junk. How can we describe that? So let's do two things. Let's put that line in again. We've seen that one before. Okay, here we have a point. I'm going to do a point right down here instead. Okay? What do I have? I have the deviation of the line around the overall mean, and I have the deviation of the point around the line. Here I've got the deviation of the line around the overall mean, and I've got the deviation of the point around the line. Do you see a potential avenue for exploring which line is significant and which isn't? What did we do in analysis of variance? We analyzed the variance. Can we do that now? Oh, heck yeah. What did we do before? When we had ANOVA, we had this situation. We compared the variation of the treatment means around the overall mean, and then we compared the variation of the observations around the treatment means. Similar situation here, same thing. Okay? So this is our epsilon. What's this? So I actually have three things, don't I? I also have that. Well, what did you do in ANOVA? Well, in ANOVA, let's refresh our memories. We looked at that variation, and we compared it with that variation, and then we had this total variation in there as well. Okay? It's exactly the same thing. How did we partition the variance in ANOVA? We said we had y equals mu plus alpha I plus epsilon. So there was our epsilon. There was our alpha right there. And what we said was that if alpha is big compared to epsilon, then we have a significant difference. Do we have epsilon here? Yeah, you bet, right there. Do we have an alpha kind of thing? Sure we do. It's that. All right? Same thing. Now what we're doing is we're comparing that variation to that variation. So all we're doing is this. let's call this line here y hat. The hat means we're estimating that line, okay? So we're looking at this term right here. That term is going to, the variance associated with that is going to be the sum from I equals 1 to n of yi minus y hat quantity squared. That's the deviation of the point around our predicted line, which is equal to the sum of yi minus b0 minus b1 xi quantity squared. Hey, did you see that before? Yeah, you did when we wrote the normal equations. All right. Now, yi minus y bar quantity squared is equal to what? That's the total variation, right? This is the error variation. So the only other thing we need now is the variation that's associated with the model, okay? So now what we want is we want the sum of the deviation of the fitted model around the mean. So that's going to be the sum of yi hat minus y bar. Squared. So that's going to be my model variation. So graphically then, I'm looking at this. That term, that distance right there is my SSR. That distance right there is my SSE. And then that distance right there is my SSTO. There's my total variance, my error variance, and my variance attributed to the regression. So this is SSR, the sums of squares of regression. Well, that's just too damn easy. Because now you realize that what we're going to do is we're going to make a table. Source, sums of squares, degrees of freedom, mean square. Hey, you've seen that before? Our terms are going to be model, which is the same as what we mean by SSR, right? Error, and total. In other words, we're just going to write down another Anova table. And what we're going to put here is the sum of squares. There's the one that goes for error. There's the one that goes for the total. There's the one that goes for the model. Write down the degrees of freedom. Divide the sum of squares by the degrees of freedom. Get the MS. And then do the F test. And we're home free. It's that easy. Man, that seems like an awful lot of work to end up with such a simple, obvious solution. but it's pretty profound. The guys that figured that out, right, it's pretty spectacular. If you really, it's so obvious, it's so simple, it's so, I mean, yeah, sure, I mean, you don't even question it, but yet, until that was figured out, I mean, we were like babes in the woods. It's a pretty profound statistical step, okay? And the best part of it is, you look at it and you realize all you're doing is an analysis of variance, and you're just you're divvying up the variance exactly like you did before, and the only thing that's different is how you got that line. That one change, the only difference between this and ANOVA is the fact that we say we know what the nature of the relationship is. It's this line. And we know how to get the line. We know how to get the slope, and we know how to get the intercept. And it turns out that getting the slope is easy, and getting the intercept is easy. And it gives you the least squares solution, the best possible solution by calculus. It's awesome. Then you look at a program like Excel, and it'll compute the line for you. It'll give you the R square, but will it give you the Anova table? No. Not in an intuitively obvious fashion anyway. You have to work to make your own Anova table. There it is. All right, so what we're going to do over the next 4 weeks or so is the following. We're going to work with regression a little bit, and then we're going to expand regression. We're going to do a couple of things. We're going to do this kind of regression, then we're going to do something called a spline. Then we're going to do, we're going to step away from the spline. We're going to use indicator variables. We're going to do a logistic regression. We're going to do polynomial regression. And we're going to do a time series. And that's when we will look at the stock market. We're going to do a time series, which is also referred to as autoregression. That's going to take us about 4 weeks to do. These tricks that you learned here, particularly with indicator variables and splines, oh, there's one more in there, and that is we're going to do stepwise. What you learn right in there is going to have the broadest applicability to anything you do in your research program. Most students end up using one or more of these techniques in their thesis. After that, we're going to step away from regression, and we're going to do a couple of multivariate techniques. We're going to do principal components analysis, which is another one of those basic techniques that every biologist should have in their toolkit. And we're going to do discriminant analysis. So we're going to do PCA and then DFA, discriminant functions analysis. If we have time, we'll do canonical correlation, but my guess is we won't get that far, but that's fine. This stuff right here is probably the most important stuff you'll get out of this course, aside from box plots, and then followed by PCA, and then if you're ecologist of any flavor, or epidemiologist of any flavor, you'll end up doing a lot of discriminant functions analyses. All right, that's all she wrote for today, kids. No homework assigned for today. For next week, there is the two-way ANOVA. The data will go up, and the little video about the two-way ANOVA will go up today or tomorrow. It should take all of about 3 minutes to run that analysis and turn that in. That's another freebie points. Remember, we don't do exams, it's just homework, so make sure you get your homework in and you're good to go. All right,